Building parts from a powder. It's a method called additive manufacturing. Think of it as 3D printing using metal powders as the ink. Our guest today explains why this is the future of manufacturing in a range of industries. So, how does this cutting edge technique create critical parts for aircraft and other machinery? That's next on this episode of Technology Today. We live with technology, science, engineering, and the results of innovative research every day. Now, let's understand it better. You're listening to the Technology Today podcast presented by Southwest Research Institute. Hello and welcome to Technology Today. I'm your host, Lisa Benya. Additive manufacturing is an up-and-coming method of building complex parts for big machinery. We're talking aerospace and automotive to biomedical and energy applications. It is a process still under development, but brimming with possibility. Parts manufactured this way are already in use on airliners. Our guest today is Southwest Research Institute engineer Grant Musgrove. He's on the front lines of taking additive manufacturing to the next level and overcoming the challenges of this fairly new technology. Thanks for joining us, Grant.
Yeah, thank you for having me.
So, Grant, let's start with the basic definition of additive manufacturing. Explain this term for listeners hearing it for the very first time.
Well, I guess if we break it down, additive manufacturing, we are making something, we're manufacturing something. Most people know what that is. And additive, a great way to explain that, I think, is to look at the complete opposite of that, which would be subtractive. And that's what we usually use to make things. It's called conventional manufacturing, which is basically taking a big hunk of material and removing it until you get the part that you want. So additive would be starting with some kind of base material and then building it layer by layer until you get the part that you want.
So in some cases, it's a powder you start with, and then that forms into a part, whereas in subtractive manufacturing, as you said, you start with this chunk of metal and it whittles it down or carves it down into your desired part.
Exactly.
Okay, so how long has this type of manufacturing been in existence? Because additive manufacturing is fairly new.
Yeah, it's been getting a lot of attention over the past, I would say, 5 years or so in the media, but it's actually a technique that's been around for decades. The older technology is really on plastics, like an ABS plastic, or there's other methods like SLA, stereolithography. Basically, you start with a big tub of a fluid and use a laser to solidify that fluid layer by layer until you get the part that you want. This has been used a lot for prototyping. If you want to actually see the part, then you can build it with a plastic. You can build it in this way or with just plastic pellets, and then you heat it up to a liquid, and then you kind of melt it together layer by layer. That's generally how it's been, is to simulate, okay, this is what the part is, so I can put my hands on it, I can take a look at it, look for problems with the design before I go and make a very expensive part. So now, over the past probably 10 years, things have moved into metal additive manufacturing, which is not to make, you do want to make prototype parts, but your goal isn't to make a part, understand it, and then make it a totally different way. Your goal is to make a part a couple at a time, and then you can better understand it. And then the future would be to actually just print the parts, especially if it's very complex.
So can you save that, formula to make a specific part and then print as needed?
Yeah, I think that's the ultimate goal of that. That's still many years away to basically just print and use. The way things are printed now, there's so much study and research going into all aspects of it, the powders, how you actually print it, how you design it for printing, and then what do you do after printing.
So the term additive manufacturing doesn't lend itself to sounding exciting, but this really is an exciting time in manufacturing. Why? Can you give us a little more insight on that?
So it's an exciting time because we get to look at things that we've never been able to look at before. And I know that sounds very generic, but for instance, if I wanted to, heat exchangers. Heat exchangers. If you think of one, you think of a big pipe with a bunch of little pipes in it, and you're exchanging heat between two different fluids. That would be called like a shell and tube heat exchanger. But what if I wanted to make a very, very, very small heat exchanger? And when I do that, I can exchange a lot more heat in a smaller volume. So that would be a lot of space savings, and that's something that I can't really manufacture conventionally because there's only so small of a hole that I can drill. And there's only so small a hole that I can drill that's cost effective. So with additive manufacturing, you would be building it with holes in it, basically, and you could make a very small heat exchanger with very small passages, which could never have been done before.
So, why is it important to start this conversation now and put this process of additive manufacturing in the spotlight? What are your thoughts?
Well, my thoughts are that I think there's a lot of misconceptions about where the technology is and what it can be used for. There's obviously the dream is to just print a part and use it. I think the idea is, if you put astronauts on Mars, send them with a printer and some bulk material, and then they could make whatever parts they want. It's not really at that stage yet. A lot of it is we just don't understand it. And that's really a big exciting part of this is there's a lot more to learn on additive manufacturing. If you think about conventional manufacturing, like cold working, blacksmith stuff, casting, things have been done for thousands of years with, bronze or iron or something like that. That's thousands of years of material science development and manufacturing development. And additive manufacturing is decades old. So that's the exciting part is we get to explore this whole new design space for how you build something. So it's very exciting from a material science perspective because you could potentially look at new materials. You could combine materials in a way that you never have been able to before. It's of interest to people like me who want to apply it to things because conventional manufacturing can be expensive or just not practical for some parts. And with 3D printing, we can do it very quickly. We could do prototypes and we can learn without going through a costly manufacturing process.
So, what is the biggest mystery, I guess, if you will, here? Is it how reliable these parts are once they are manufactured? Is there something more?
So the big unknown is how exactly you can tweak the build parameters basically to control the material strength and reliability after you print it. So with conventional manufacturing, there's tons and tons of data on if you want a specific strength, if you want a specific corrosion resistance, you can heat treat it like this, you can hot isostatic press it. There's lots of different ways to do that. But with additive, if you want to shoot a laser at a bunch of powder and make a part, there's a lot of unknowns on what kind of laser intensity, what size of layer do I need to do? Is there something that I can do to control the strength of the part or the corrosion resistance of it? And you want to do all that as you build the part because ideally you want to get to the point where it comes out of the printer, you slice it off the build plate, and then you install it.
Okay, so describe, you just did a little bit, but describe the process of manufacturing a part with this technique. So you do start with some powders and some lasers and you end up with a cool part, but what does that whole process look like? How long does it take?
I think probably the easiest way to explain it would be welding. So for instance, the machine that we have here at the Institute is a Renishaw AM250. So that uses powdered metal, so titanium or stainless steel or Inconel materials, which are a high nickel super alloy used in gas turbines. So you're basically starting with powder and welding it together is the easiest way to explain it. Everyone knows a welding process where you basically put down a bead of material. You're trying to connect two pieces of metal together and you lay down a bead and you kind of fill the gap between the two and you melt locally the material that you're trying to combine together. So if you think of laying down a bead of weld and then a weld bead on top of that and then on top of that and then on top of that, you could build up a part. That's what additive manufacturing is doing on a very tiny scale. You're building up a weld bead that is a couple thousandths of an inch thick.
Okay, so, and if you could explain a little bit about the machine that's used, it does have lasers, and this is a pretty big piece of machinery.
It is. I would say it's about the size of a wardrobe closet, and there are lasers in there. Lasers make everything sound a lot more exciting. It's futuristic, and this machine certainly does have that. So basically, what's happening is you start with a build plate, which is just simply a big, thick plate of metal. That is where you start the process. You have to build on something. You can't build off air. So you start with the big hunk of metal, and then the machine actually puts down a very tiny layer of powder, which you could change depending on how you want to build it. And then you shoot a laser over the pattern to create the part you want. If you wanted to make a square, you would shoot the laser in a square shape. If you wanted to do a solid square, then you would fill all the material in with the laser. And that would create one layer that is thousandths of an inch thick. And then you would have basically a windshield wiper come over and move another layer of powder on top of that. So now you've got your first layer of part, a little bit of powder on it. You're going to shoot the laser on it again to build that next layer, and that's going to melt the powder to create your new layer, but it also slightly melts the powder, or that layer that you just made, it melts that underneath so that they can solidify together, and layer by layer you're building a part.
Okay, so you brought in a show and tell piece, which I love. This is a little impeller I have in front of me, and it's about, maybe 2 inches?
About 3.
3 inches wide, and it looks pretty complex. So tell us about this part. Was it, I guess, difficult for the machine to build? Is this one of the, because you mentioned a square, but this is definitely more involved than that.
What this piece is we basically printed an impeller with our machine here at the Institute, and we sliced it up so we could take a look at what's inside. So it's about a 3-inch diameter impeller. It is designed to go inside of a small gas turbine that fires at about 780 Celsius inlet temperature. So what is it, like 1500 F? So it gets pretty hot, and it spins at 120,000 RPM, so it has very, very high tip speed. This is, I would say, a very challenging design, and it's something that we really wanted to start with. But what I have here is a basic radial inflow turbine wheel, and it has 2, 4, 6, 8, 9. It has 9 blades on it, and one of the things that we were trying to understand is, can we actually make something like this? We know that there are gas turbine blades that are a single blade that are being made with additive manufacturing. There are some complex parts, but can we actually build an impeller doing this? And surprisingly, we were able to do it first shot. We built a quarter section. It turned out very, very well. We were able to reliably build the blade sections without any supports, and it came out very, very close to what we expected from the solid computer model of what we built it as. But what makes this impeller unique is that we're using additive manufacturing to accomplish something that conventional manufacturing can't do, or can't do very easily. So what we're trying to do is add internal cooling channels to this impeller. So that's done a lot in gas turbine blades. It's usually cast in is the typical approach. And that approach has been applied to a radial wheel, but what makes a radial wheel much more difficult is, instead of casting one blade, you're casting 9 blades at a single time. So if one of those is misaligned, you have to scrap the whole part. And so it's a very high risk part to investment cast. So no one really does that. So that's why it's perfect for something like additive manufacturing, where you're not trying to cast 9 different blades. You're just building a part just like you're building any other part. You're just building it with holes in it.
Yeah, so this part is actually a little bit of a wonder for you guys in your area. And what's next for it? I mean, are you distributing these parts, or are they just kind of there for research purposes at this point?
So these parts we're making these under an internal research and development program called Makers that we're doing here at the Institute. And this is one of a number of projects that are looking at how we can use additive manufacturing here at the Institute. Because we have our machine, we want to learn how to use it. We would need to better understand it and apply research that, in some cases is a little bit risky that either the government or the industry isn't ready to fund yet, but it's something that we think is important to look at to hone our skill set. So this is one project. I would call this on the application side of the project, where we want to utilize additive manufacturing to overcome a problem with conventional manufacturing. There are other levels of this. There's one project where we're trying to understand how you actually evaluate the part. Once you build it, how do you know it's a good part? So there's one project looking at that. There's another project looking at how do you understand how the part is built during the process? Because as you're shooting these layers with heat, you're basically creating thermal stresses in the part. And so because you're heating and it's cooling at different rates, and depending on where your laser's going, you can have certain parts that are stressed, and that can cause a problem when you want to go remove it from the build plate, or it could cause deformation during the build. And one project is trying to better understand that and predict that. And then to go back one more, as far as the powder, the most basic element of what you're trying to build things out of, it's usually spherical powder because that's commercially available. But we have one project where we're looking at hexagonal powder, platelets, basically. So you get a more uniform structure of your build powder, which could benefit your build to help with some of any of the splatter from the laser, because again, you're basically welding. Or also if you wanted to tune your powder to improve your build.
So are you talking about the shape of each grain of powder, whether it's circular or hexagonal?
Exactly, yeah.
That's detailed.
It is. Yeah, we've developed a new process for that. For building it, we're manufacturing it on a small scale and actually getting some pretty good results. It's very interesting to see how we can reduce that splatter during the weld process using platelets.
So going back to the machine that is used, it is costly, but in the long run, can you give us a cost estimate on how much a machine like that would cost?
I could say hundreds of thousands of dollars, but I wouldn't know if that's accurate. I could say it's less than $1 million for sure. But as far as is that valuable to us? I mean, it certainly is, because really we're an independent research organization, and so we do a lot of prototypes, basically, especially within our machinery department. And so to have the capability to build a prototype here on campus and then test it out saves us an incredible amount of time in outsourcing for conventional manufacturing. Just the process that takes to outsource it, build it, receive it back, and then install it. We can build a part in a few days and have it available to us if we need to.
So over time, does this method save money over traditional manufacturing if you have one of these machines as a company?
It can. It really depends on the type of part that you are building. So if you want to make something simple, additive manufacturing is never going to be cost effective. Powder's expensive. Time in the machine, you can only build so many depending on how big your machine is. So conventional manufacturing is much, much cheaper on a big scale. I know that the long term is to see additive on a large scale production type approach, but that's still a long ways off. So additive really gives you that value of a quick turnaround for one-offs, a prototype, or a small batch of something.
Okay. So what are the benefits of additive manufacturing over traditional or subtractive manufacturing? We've talked about a few of them already, but if you could make a list.
Some of the benefits of additive manufacturing.
Over subtractive.
It's really just customization, I would say. Customization, optimization. What's the bare minimum I need of material to make this part work? Can I add a little bit of material in one area to make it last longer? That's a big benefit. The other, customization, if you want a part to fit one particular, maybe if, for example, if I had some machine that was built 60 years ago and something breaks on it, the company who built it is no longer in operation. I can't get spare parts unless I find a used one if I'm lucky enough. So I really have no option for a repair part, and maybe making a single repair part conventionally just isn't worth it.
So that's really cool that you can take an old part and rebuild it with additive manufacturing. And that's actually been done before. Is that correct?
Yes.
Do you know
I-
what situation?
I know that a lot of companies are looking at that for like offshore, like when you don't have access to spare parts, you can make your part there. Or when you're, out on the North Slope of Alaska, there's just not much out there that's available. The other is because if you think of like something like an airline, they are maintaining aircraft engines, so which are made up of many, many, many complex pieces. So the idea there would be to make specific parts one at a time, or repair parts using additive manufacturing.
So where are we in the development of this process? How long until it becomes mainstream?
Yeah, I think for say like plastics and prototyping, it's definitely there. You can buy these off of, I think, Amazon. You can get some of these 3D printing machines. But for the metal parts, that's tough to speculate how long that would take. Like I mentioned, there's thousands of years of conventional manufacturing experience, and we've got a couple decades of this experience where there's a lot of research that needs to be understood on how to make these parts.
And what about reliability? We touched on that a little bit, but how do you test that parts made in this method are as reliable as conventional methods?
Well, conventional methods, if I was going to make a part using that, I would make a test specimen, say like, looks like a cylinder, kind of like a dog bone. And I would put it through a series of tests and then see how long it lasts. And I would do the same thing for additive manufacturing. The big difference is with the conventional test is I start with a big hunk of metal and then I machine it down to my test specimen. And then I put it in a machine and basically pull on it and push on it to compress and stretch it many, 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 many times, maybe thousands and thousands of cycles, and then see how long it lasts. To do that with additive manufacturing, I would just print a cylinder of that shape and then install it and then do the exact same thing to it and see how long it would last. The difference being with conventional manufacturing, I can vary some of those properties, durability with how I heat treated and other post-processing techniques. Additive manufacturing, you have that same option. You have heat treatment, other post-processing techniques to make it last longer. But then you also have how you're building it that can make it last longer. So there may be an area where you could improve durability at the build process.
Okay, so we're talking about two steps here. One is making it reliable as it's being built, strengthening it as it's being built, which is the goal. And then there's the post-treatment where you can heat it and do other things to make it stronger and more reliable.
Right.
So there's a two-part process in making a part reliable.
There is, and I think part of that is because we're trying to apply our understanding of conventional manufacturing methods to additive, because it's all we have to start with. So with additive, we'll build something, and there's gaps in it, basically. There's pores. So how do we fix that? Well, we know how to fix that in conventional techniques is we do like a hot isostatic press, put it under a lot of pressure and heat, and then we can kind of solidify, close those pores, and we can control grain structure, grain growth. That's always after the fact. Where we are not yet is to control that during the build process. And once that's available, then I could see us not even doing the post-processing techniques anymore because they won't be needed.
So are we successfully producing reliable parts with the processes we have in place now using additive manufacturing?
Generally, yes. These parts are being flown on aircraft engines. So blades, internally cooled blades, combustor nozzles are being used as well. And those have to be proven to be reliable by FAA regulations or they cannot be installed. And so this is happening, it's just not happening on a big scale, and there still has to be a lot of research into proving that it will last.
So the additive manufacturing technique goes beyond just making parts for machinery. There are also some biomedical applications. What can you tell us about that?
Yeah, and the great thing about additive manufacturing here is because it is customizable, like I mentioned earlier, because instead of having a biomedical part like a new hip joint or something that is supposed to work for most people, you can actually print a custom one that will fit exactly where your bone structure is. And so you can tailor the attachment points to your body.
So that's really cool that something you print out of this machine can actually be useful and can help you medically. Mm-hmm. It's pretty amazing. For you in particular, what is your vision for additive manufacturing one day? Do you see it going further, really kind of becoming, as we talked about earlier, mainstream?
I think so. My vision of it, and this is just me speculating, I don't know if this is something within the next few decades that you'll see, at least a metal machine, that you'll see and everyone will have one in their house. It's expensive. I mean, you're talking about lasers, you're talking about metal powders that can explode. There's a lot of safety issues that go with this. So I think that what we'll see is a lot more additive manufacturing parts on the initial design phase of a part, and rapidly turning around a part design much quicker now.
And I love that whole customizable aspect of it. That's really what makes it cool. And there are a lot of positives to it, and there are a lot of kinks still being worked out and challenges to overcome. But are there any ethical debates brewing at this time over 3D manufacturing? I think I've read a couple of articles about the possibility of 3D printing guns and, people maybe not using 3D printing for the right reason. So has that come up at all? Are you aware of?
Here at the Institute, we really haven't tackled some of the ethical considerations because we operate under a general code of ethics anyway in all the work that we do. So it's not really different than what we typically do. But yeah, I've heard the 3D printing guns, and then you can't track it, and there's problems with that. But my viewpoint on that is there's ethical considerations in both directions. You can consider and think that it's going to be used for evil and make guns or weapons or something, and then you can outlaw it, but now you're taking away all the benefits that it could do, like with medical devices, customizing things, making, eventually body parts out of additive manufacturing with these things. So I think just with any technology, there's good and bad to it, and it's just something that needs to be
sorted through
yeah.
And overcome. And yeah, there's definitely a lot of great possibilities with this exciting technique for manufacturing. So we want to mention an upcoming webinar, Introduction to Additive Manufacturing in Turbo Machinery Applications. What does this online course cover?
Nathan Andrews, a colleague of mine, is presenting a short webinar, about an hour, that's a very good introduction for beginners. It's focused on this is how additive manufacturing is used in turbo machinery, so that includes turbo pumps for rocket engines or aircraft engines or power generating gas turbines. That's where the focus is, but it's a lot on this is what's been done, this is kind of the process, here's some of the failures, here's some of the successes. These are some things to consider. So it's a very good introduction if you are just getting into this design space.
All right, a great overview of additive manufacturing. And that's coming up Wednesday, July 17th, noon to 1, and we will have the link to register on this episode page. So, Grant, this has been an insightful discussion on the future of manufacturing and really the potential of additive manufacturing. It's an exciting time in making things, wouldn't you say?
I certainly would.
All right. Well, thank you for joining us today, Grant.
Thank you for having me.
And that wraps up this episode of Technology Today. Subscribe to the Technology Today podcast to hear in-depth conversations with people like Grant Musgrove, changing our world and beyond through science, engineering, research, and technology. Connect with us on our Southwest Research Institute social media pages on Facebook, Instagram, Twitter, and LinkedIn for the latest Technology Today episodes and much more. And check out the Technology Today magazine at technologytoday.swri.org. Thanks for listening.